In this lecture here, we're going to talk about rational functions and their graphs. So I'll do a review of exactly what rational functions are in a second, but let me break down what this lecture series is going to be about. So our objectives we're going to work through is the first thing we're going to talk about is how you find the domains of rational functions, identify what are called vertical and horizontal asymptotes. So this I'm going to break into the first video lecture. And then I'm going to follow it up. Then we're going to start talking about what the graphs of rational functions look like. And we're going to spend a lot of time on that. So the next lecture, I'm going to talk about using transformations to graph rational functions. So this is lecture 2. This will be a little bit shorter. And then what we're going to spend a lot of time on, your final lecture, is going to be how you graph rational functions. And this is a multi-step process. And I'm going to, take my time to work you through it, and I'm going to show you all the tricks and shortcuts, and it won't be too bad. And I have 3 long examples of that worked out. So this will be lecture number 3. Okay, so these will all be separate video lectures. So let's start with the first part here, okay? Domains of rational functions. So just as a recall, what exactly is a rational function? So rational functions are quotients of polynomial functions. This means that rational functions can be expressed as, so f of x is equal to what we say is p of x divided by q of x. And this is where p and q are rational functions, are polynomial functions, and q of x is not equal to 0 because you can't ever divide by 0. So for example, what some rational functions might look like, you might have something like this. X plus 2 over x minus 5. Or it can even be something like this. 4x squared over 17x minus 6. I don't know, something like that. Okay, so we want to deal with functions that look like this. All right, so the domain of a rational function is a set of all real numbers except the x values that make the denominator 0. Okay, just because, remember, you can never divide by 0. Okay, so what I'm going to do here is I'm going to walk you through how you find the domain really, really easily, and then we're going to talk about how you show what the domain is, okay, using interval and set builder notation. Okay, so let's find the domain of this, right? Okay, so find the domain of this rational function. So f of x is equal to x squared minus 25 divided by x minus 5 here. Okay, so looking at this function, ignore this part here. Okay, find the domain of this. So f of x, you have to be careful here. So maybe you just look at this and you say, wait a second, let me x squared minus 25, that's factored into x minus 5 times x plus 5 all over x minus 5. So here's the deal. The x minus 5s will still cancel out. However, if you're looking at the domain, just look at the denominator now before simplifying. So you just say, okay, well, what values would make this equal to 0? Because I can never have the denominator equal 0. So you just add the 5 over. So the domain here, you can see, look, whenever x is equal to 5, you get to divide by 0. So the domain is all real numbers. It can be anything but 5. Okay, so the way you would show this, so there's 2 ways you can show this, right? You can show it in set builder notation. So the domain, it's x such that x is not equal to 5. Okay, that's in set builder notation. And then you can show the domain in interval notation. So you would go negative infinity, and then you'd go right up to 5. So open bracket here, because that's saying go right up to 5, but don't exactly be 5. And then union, pick up right after 5 and go to positive infinity. Okay, so look, when you want to find the domain, just say, okay, when would you have the denominator equal to 0? And then it's all numbers but that. Okay, so let's try this one here. So let's find the domain of this rational function. So g of x is equal to x divided by x squared minus 25. So at first, you look where this x squared minus 25 would be equal to 0. So you can add the 25 over, take the square root of both sides, and when you take the square root to solve, you get x is equal to plus or minus 5. Okay, so it's all real numbers. Look, all real numbers, but negative 5 and 5. So domain is all real numbers. But minus 5 and 5. All right, so let me show this as set builder. All right, so the domain here, it's all x values such that x is not equal to minus 5. Also, x is not equal to 5. So very, very easily there. Interval notation is a little bit trickier. Okay, if you want to show it this way. So the domain here, you would start at negative infinity and you'd go to negative 5, okay? And then you'd pick up right at negative 5, and guess what? You'd go to 5 again, so it'd be all numbers between negative 5 and 5, and then you'd pick up at 5 and go to infinity here. So the interval notation here is a little bit harder for this. Okay. All right, now let's try this one. Let's find the domain of this. H of x is equal to x plus 5 divided by x squared plus 25. Okay, so again, look where x squared plus 25 is equal to 0. So hopefully you see here what's going on, right? Like you would move the 25 over, you'd get x squared is equal to minus 25. When you take the square root to solve, you get plus or minus the square root of minus 25, which would be plus or minus 5i. So you get an imaginary number here. So what this means is, look, there's no real numbers, right? That would get a divide by 0. So the domain here is all real numbers. So in set builder notation, you would show it like this. The domain is x such that x exists in all real numbers, or in interval notation. Well, it'd just be all real numbers, so it'd be any number from negative infinity to infinity here. All right, so the domain, just look, as I was saying, just look where you get a divide by 0. You can't have that. All right, so now what we want to talk about is asymptotes here. Okay, so asymptotes are lines. There's going to be two types. There's going to be vertical and horizontal asymptotes. So they're lines where the graph is going to like butt up against the graph but never crosses. Okay, so the line x is equal to a is what's called a vertical asymptote of a graph of a function f if f increases without bound as x approaches a. So what happens here is as x gets closer and closer to a, the graph is going to blow up right next to it like this. Okay, now this means the x is going to get just really, 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 really large. It's going to keep increasing. It's going to go towards positive infinity, but it never crosses this line. Never crosses it. Similarly, you can have the flip side here. So x is equal to a is a vertical asymptote of the graph of f if x decreases without bound as x approaches a. So what this means is, and I'll explain these notations in a second. As x gets closer and closer and closer to this value a, the graph is going to go down to negative infinity, and you can also have it on the other side. Go down this way. So what these mean, these things here. So this is saying as x approaches a from above, this plus means, so from the plus side, the graph goes towards infinity. as x approaches a from below, that's what that negative means. This is saying the function f of x goes up to positive infinity here. So you got the sound effects with that. And it's just the flip side here. As x approaches a from above, the graph is going to go down to negative infinity. And as x approaches a from below, you're going to go down this way. Now, finding vertical asymptotes actually really help us sketch the graph of these rational functions. Okay, it's like one of the first things we'll do. Okay, so here's what happens. If f of x is equal to p of x over q of x, so some rational function, in which p of x and q of x have no common factors. Okay, so like let me just go back real quick. A common factor, like here, x minus 5, x minus 5, you could cancel those out. So there's none of that in this, okay? So when you go to find vertical asymptotes, you look at a simplified rational function. Okay, so no common factors, so what that means, it's simplified. And a is a 0 of q of x, so a denominator, okay? Then x is equal to a as a vertical asymptote. So what's going on here is you look at the simplified version of f of x is equal to p of x over q of x. So you cross out any common factors. Any x that makes q of x equal to 0, okay, so you get to divide by 0, okay? You have a vertical asymptote. At x is equal to, so any x is equal to a, you have that, then that line is a vertical asymptote, okay? All right, so let me walk you through. What I'm going to do is I'm going to do 2 examples and show you what the graphs look like of the function so that you can see the vertical asymptotes. Okay, so let's try this one. Find the vertical asymptotes, if any. There doesn't always have to be, okay? So if any, of the graph of this rational function. Okay, so f of x is equal to x divided by x squared minus 1. So first off, I'm going to factor the denominator. So it's a difference of 2 squares. So this is going to factor as x minus 1 times x plus 1. No common factors. So now look, where this x minus 1, x plus 1 is equal to 0. And you see here, if you set, x minus 1 is equal to 0 or x plus 1 is equal to 0, you see that you get 2 solutions. X is equal to 1 or x is equal to minus 1. What that means is, thus we have 2 vertical asymptotes. Okay, the first one would be at x is equal to negative 1, and then the second one would be at the line x is equal to 1. And look, let me show you what the graph looks like here. Okay, so the zeros of the denominator are negative 1 and 1. So what that means is when we go to sketch the graph, I'm going to go to x is equal to negative 1. I'm going to draw this dotted line up here. Okay, that's the first vertical asymptote. Okay, that's that line x is equal to negative 1. And then I'm going to go to x is equal to 1, and that's the second vertical asymptote. And then I'm going to show you, eventually I'll show you how you would end up sketching the rest of this. Okay, that's where we're going towards. It's like after you find the vertical asymptotes, like what happens next, okay? All right, let's try this, and just so you could see here. Okay, so let's find the vertical asymptotes of these rational functions. So this one here, all right, g of x is equal to x plus 3 over x squared minus 9. So if you want to find vertical asymptotes look, you look at this and you say, okay, well, look, the domain, obviously x cannot be -3 or 3, okay, because that would get a divide by 0. But I'm going to simplify here. And I'm left just with this, okay, after I cancel out the common factor, okay. I'm left with 1 over x minus 3. So look, x is equal to 3 would then be the vertical asymptote. So when you go to sketch the graph, you'd go to x is equal to 3 and you draw this dotted line. Now notice we're saying, look, you still cannot plug in -3. So what would happen is when you go to sketch the graph of this, there would be a hole, all right, in the graph corresponding to this, okay? It would be like, well, when I get to -3, there just has to be a hole. It has to be a hole there. And then I'd keep going on with the graph. But there's only one vertical asymptote here. So even though in the unsimplified version, 2 values of x would cause a divide, excuse me, a divide by 0, excuse me, when you go to find the vertical asymptotes, only look at the simplified version. So here, let's look at this. F of x is equal to x squared minus 4 divided by x minus 2. So look, again here, the domain, x cannot be equal to 2. But when I simplify this, right, you're canceled out and you're just left with the equation x plus 2. So there's no divide by 0 here. So when you have this, there's no vertical asymptote. And then, so when you were to sketch the graph of this, you obviously, when you sketch the graph of x plus 2, it's just a linear function here, and there would just be a hole in the graph where x is equal to 2, because you still cannot have x is equal to 2. All right, and don't worry, as we continue through this, we're going to practice still more and more with these graphs. So this is just identifying the vertical asymptotes first. All right, horizontal asymptotes, a little bit harder. Maybe not, but there's a process for it. But let me give you a definition of this. So the line, now it's y is equal to b, is a horizontal asymptote of the graph of a function f if f of x approaches b as x increases or decreases without bound. So what that means is, look, as you increase x, okay, x gets larger and larger and larger in value, the function just approaches this line y is equal to b, and it'll never cross it. So you can have it come from below, above, or you can have it actually cross, for small values of x, but just as x increases without bound, it's going to have to go this way, come up really, really close to the line. All right, and it's the same thing as x goes to -infinity, you can have it. But so let me show you the process of finding the horizontal asymptote. So the horizontal asymptote is a horizontal line here, y is equal to b. All right, so let's let f be a rational function given by this. Okay, so this is just the polynomial definition, all right, in both the numerator and denominator. So what's really important, the only thing you have to really care about, okay, is you need to know the degree of numerator. Okay, we'll call that n. And you need to know the leading coefficient. And that's a sub n. And then you need to know the degree of the denominator. That's m, and the leading coefficient of denominator. Okay, that's b sub n. So here's what you do. You compare the degree of the numerator to the degree of the denominator, okay? If n is less than m, so what that means is the degree of the numerator is less than the degree of the denominator. The x-axis, or y is equal to 0, is the horizontal asymptote of the graph, okay? And don't worry, I have an example of each of these. If the degrees are the same, so if n is equal to m, the line y is equal to a sub n over b sub n, so the ratio of the leading coefficients, is the horizontal asymptote of the graph. And if the degree of the numerator is greater than the degree of the denominator, n is greater than m, the graph of f has no horizontal asymptote. Okay, so here's what you do. You look at the degrees, okay? And then if the degrees, if the degree of the numerator is less than the degree of the denominator, x-axis is the horizontal asymptote. If the degrees of the numerator and denominator are the same, the horizontal asymptote is y is equal to the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, graph has no horizontal asymptotes. All right, I know it's a little confusing. Don't stress. We'll show you an example of each so you can see it. Okay. So let's find the horizontal asymptotes if there is one of the graph of each of these functions. Okay, and then I'm going to actually show you what the graphs look like so you can verify and see this. Okay, so in f of x, this first one here, it's 4x divided by 2x squared plus 1. So look what's going on here. The degree of the numerator is 1. And the degree of the denominator is 2. Well, so just so we're clear here, this is my n and this is my n. And we see that n is less than m here. So what's happening here? Y is equal to 0 is the horizontal asymptote. Boom, we got it. B, let's look at the second one. G of x is equal to 4x squared over 2x squared plus 1. Degree of numerator, it's 2. That's my n. The degree of the denominator, that's also 2. That's my m. So we see here that n is equal to m. The degree of the numerator is the same as the degree of the denominator. Boom, boom, boom. When n is equal to m, the line y the y is equal to a sub n over b sub m, ratio of the leading coefficients, is the horizontal asymptote. So this has a horizontal asymptote at y is equal to, leading coefficient is 4 over 2, which is 2. And then finally c, h of x is equal to 4x cubed over 2x squared plus 1. The degree of numerator here is 3. The degree of the denominator is 2. And we see here that n is greater than m. So when that happens, no horizontal asymptote. And I'm going to show you in this next slide here what the graphs now of each of these look like. And look, you can see here, this is our first one. When you were to sketch this graph, even if you plug this in your graphing calculator, as x increases, what would happen is this graph would get closer and closer and closer on both sides to y is equal to 0. This graph here, we said the horizontal asymptote was y is equal to 2. So as x increases without bound, what would happen is you'd see this graph would get really close to this line but never cross it on both sides. And here we said there was no horizontal asymptote, so x is going to increase. Or as x increases without bound, our function also increases without bound, and as x decreases without bound, so does our function here. And what we're going to be building towards is you're going to see that we're going to use this information. We're going to use this information to help us sketch the graphs of these rational functions by hand in the coming lectures.